Next, you are asked to analyze the first floor substitute frame of B1 to 4 using the moment distributions method. The questions ask you to assume that the load is maximum throughout the continuous beam. First of all, you will need to refer to the structural key plane. We are talking about frame B here. By referring to the elevations, the first floor substitute frame will constitute this part, as indicated by the frame here. The story height, it will be 4 meter and 4 meter. The beam span, it will be referring to the structural key plane, 5.6 meters, 6 meters, and 5.6 meters. 5.6, 6, and 5.6 meters. The beam size is given in the structural key plane, which is 200 times 450. As for the column size, 200 times 200. The questions ask us to assume that the loads will be maximum throughout. We have calculated the maximum loading previously. Maximum load can be calculated from 1.35 GK plus 1.5 QK. The loading on the first floor, it will be 9.79 kN per meter. That means the UDL acting on the beam here, it will be 9.79 kN per meter throughout. To do the moment distributions method, we will need to first determine the stiffness of every sections of the member, including the columns and the beams. The higher the stiffness of the member will carry higher degree of moment, assuming that the moment taken by different sections of the member, it will be proportional to its stiffness. Therefore, we will need to first calculate the stiffness. You may use the equations stiffness K equals to EI per L to determine the stiffness of the beams and the column. The equation will require the moment of inertia as well as the span of the member. Therefore, you will need to calculate the moment of inertia, which is given in the equations of BH power 3 of 12. The beam size is 200 times 450. The I will be calculated by 0.2 times 0.45 power 3 divided by 12. That gives you this value. As for the column, the I will be calculated as 0.2 times 0.2 power of 3 divided by 12. That gives you the I for the column. Here we assume E is equals to 1. As the grade of the concrete, it will be the same throughout the entire structure. You may choose to use the actual E, which is the modulus of elasticity of the concrete. However, at the end of the day, when we are computing the distribution vectors, the E shall cancel out each other. The distribution vector will be the same. Now, if you choose to use the actual E, you will need to get the concrete strength, which is FCK equals to 30 Newton per mm square, and then refers to table 3.1 in Eurocode 2, concrete grade 30. The E shall be taken as 33 gigapascal. For simplicity, maybe we just assume the E equals to 1. Now you have the E and you have the I. You will need to substitute the length of the members into the equation. First, we determine the stiffness of this beam here. We call it KAB. It is determined by having the E multiply the I of the beam divided by 5.6 meter span. As for the second stretch here, KBC shall be equals to E multiply the I of the beam divided by the span 6 meters. That gives you this value. You will do the same for the columns. E times the I of the column divided by the story height, which is 4 meters. That gives you this value. Now that you have the stiffness of each members calculated, you're going to put the stiffness into the table here. First, you will need to construct the table. For the subframe here, you will have 4 joints, A, B, C, and D. There will be 4 joints, A, B, C, and D in the table. For joint A, you will have columns and a beam. You combine these 2 columns together. That gives you the columns and the beam. We write this as the beam AB, as we are talking about this beam from A to B. Now let us put in the stiffness. The stiffness of the beam AB, it will be this 0.0027. Here the value is being rounded up. As for the column here, you are talking about the upper column and the lower column. This will be the stiffness of the upper column, and this is the stiffness of the lower column. We lump both columns together. That gives you a total of 6.67 times 10 of power negative of 5. Next, we look at the joint B. Joint B is here. You will have column at the center, beam BA, and also beam BC. That gives you the column at the middle, beam BA and beam BC. You will repeat the process for the joint C and D. Once you have the stiffness filled out, now you will need to determine the distribution factors. By looking at the diagram here, you have one stiffness for the beam and another stiffness for the column. Whichever moment acting at this joint here, it shall be shared between the beam and the column. We mentioned that the amount of moment taken by the members, it will be proportional to their stiffness. The larger the stiffness, the more moment it is taking. Therefore, we're going to quantify the total stiffness in order to determine the distribution factors. The distribution factors for beam BA, it will be equals to the stiffness of beam BA divided by the total stiffness of both columns and beam. That gives you a distribution factors of 0.8. You will do the same to determine the distribution factors for the column, which is get the stiffness of the column divided by the total stiffness of both, then you get 20%. It means that whichever moment acting at joint A here, the beam will take 80% of the moment, whereas the column will take 20% of the moment. Next, you will proceed with joint B. Joint B here, you have columns, you have beam BA, and you have beam BC. Each of them will have their own stiffness. You will need to determine the distribution factors of each of them. To determine the distribution factors of beam BA here, you will get the stiffness of beam BA divided by the total stiffness of all members at the joint. That gives you 46%. As for the column, get the stiffness divided by the total stiffness of all members at the joint, you get 11%. You will do the same here. Same process goes to the joint C and joint D. Now if you refer to the frame structure here, based on the dimensions given, you know that it is symmetrical. That means whatever you calculated at joint A and joint C, there will be a mirror at joint C and joint D. Knowing it to be symmetrical, whatever value that you calculated here, it shall be used at the joint C and D. This can speed up your calculations process. Next, we determine the span. The span between A to B here, it would be 5.6 meters, 6 meters, and 5.6 meters. In terms of the loading, the question asks us to assume the maximum loads throughout. And the maximum loads for the first floor, it would be 9.79 kN per meter. That gives you the UDL 9.79 kN per meter throughout. As for the total load, it will be the UDL multiply the span. Then you get these values. Next, we need to calculate the fixed end moment. You can imagine like this. You have an UDL along the beam span here. Since you're going to assume the members here, it will be continuous throughout. That means you're going to expect the bending moments something like this. This shall be considered as the fixed end moment. Let's say now you have a UDL here. It will generate moment here, and this moment is going to be the fixed end moment for this span. As for the intermediate span, the UDL is here. This is going to give you the fixed end moment, this and this. Now how do we calculate the fixed end moment? For a continuous member, the equations for the fixed end moment, it will be equals to W L square per 12. This is the W UDL, L square divided by 12. That gives you the fixed end moment 25.6 for the entire span between A to B. As for the internal span, the fixed end moment, it will be W times L square per 12. That gives you this value, 29.4. As for the other side, it will be symmetrical. Based on the fixed end moment calculated, you know that joint A, you will have 25.6 kN/meter moment. There is no adjacent members contributing any moment here. That means the entire 25.6 kN/meter fixed end moment will have to be fully absorbed by the columns and the beam. We know that the stiffness of the beam is greater than the column. Therefore, the beam will take more moment than the column. Based on the distribution factors here, the beam will take 80% of the moment, whereas the column will take 20% of the moment. Therefore, out of this 25.6 kN/meter moment, 80% will go to the beam and 20% will go to the column. Next, we look at the joint B. Joint B is this. The fixed end moment due to the span here is equals to 25.6, whereas the fixed end moment for the span here, it gives you 29.4. Imagine now you have the moment this side and you have moment on this side. Both moments will cancel out each other based on the values given. This moment is slightly greater than this. Now the balance of the two moments here, which you take 29.4 minus 25.6, the balance of the moment shall be shared by the beam and columns at joint B. Now how are they going to share the moment? It will be based on their stiffness. The greater the stiffness, the larger the moment it is taking. That gives you the distribution factors of 46%, 11% and 43% for beam BA, columns and also beam BC. With that, you will get the balance between the two moments here. Multiply 46%, you get 1.7. Same process, get the balance of the two moments. Multiply 11%, you get 0.4. And then the balance of the moment, multiply 43%, you get 1.6. You will repeat the same process for the other joints. Now that you know the moments to be taken by the members. Next, the moment taken by the member here shall be carried over to the opposite side. Taking this as an example, 20.5. After distributing the moment to the beam here, this part of the beam will take 20.5 kilonewton meter. Due to the moment here, you will assume half of the moment shall go to the opposite. That's why you will distribute half of it to the opposite. That gives you 10.25. You will do the same for the other moments. You have a moment here, carry over to the opposite. Moment here, carry over to the opposite. During the carryover, you will multiply 0.5. Now this will be the moments to be distributed between the columns and the beam. Again, use the same distribution factors. 80% go to the beam and 20% goes to the column. Same process go for the joint B here. You have two moments here. Whichever balance, it shall be multiplied with the distribution factors. You get this. Multiply with the distribution factors, you get this. Multiply distribution factors here, you get this. You're going to repeat the same process for the other joints and then do the carryover process again. Repeat this process, getting the distribution factors to be multiplied with the balance and then carry over until a minimum moment can be carried over. Now if you are looking at one decimal place, you may stop at 0.1. After that, you will sum up the entire column here. That will give you the moments carried by different members. Based on the result here, the upper and lower columns will take this amount of moment, whereas the beam AB will take this amount of moment. As for the joint B, the moment taken by beam BA, the moment taken by the column, and also the moment taken by beam BC. Repeat the same process, you'll get the moments for every single members. Now that we have completed the moment distributions methods table, we have now the moments acting on each members at different locations. Our next step, it will be to acquire the shear force and the bending moment diagram. First, let us look at the first stretch of the beam. We are referring to this beam here. Based on the table, one end of the beam will have 5.6 kilonewton meter, while another end there will be 32.4 kilonewton meter moment. You're going to bring those values into the free body diagram. Get the UDL, get the span. Use the principle of static equilibrium for you to work out the reactions at both ends. The reactions at both ends shall be taken as the shear force acting onto the member. And then, based on the shear force diagram here, you can calculate the mid-span moment. Taking sigma m equals to 0 here, you will get your reactions here equals to 22.6 kilonewton. Taking sigma m equals to 0 here, you will get the reactions equals to 32.2 kilonewton. Based on the UDL, you can calculate the distance where the shear force diagram intersect at 0. This is calculated by dividing this 22.6 kilonewton with 9.79 kilonewton per meter. This gives you 2.308 meter. The area for the triangle here shall be equivalent to changes in terms of the moment. The maximum moment should fall at the locations of 0 intersections of the shear force diagram. The moment start here at negative 5.6 kilonewton meter plus the area of the triangle here, which is half times 22.6 times 2.308. You will get 20.5 kilonewton meter. In other words, this changes here, it will be equivalent to the areas of the triangles. Now, if you add this with the areas of triangle, you will get this. Next, you will repeat the same process for the following beam spans. Referring to the beam span between B to C, we are looking at these two columns here. For the beam BC, you will get the fixed end moment 31.3. Draw the free body diagram here, your UDL, your beam span, and then use the principles of static equilibrium to find the reactions. The reactions will give you the shear force acting at both ends. Use the shear force here divided by the UDL. You will get the distance where the shear force is equals to 0. In fact, since this member is symmetrical, the moment at both sides it will be the same, and the UDL will be the same throughout. You will know that it shall intersect at 0 exactly at 3 meters, which is at the midspan of this member. The little decimal here, it could be due to the decimal places, while you are calculating using the static equilibrium formulas. And then the area of the triangle here shall represent the changes in terms of moment. You will use this value plus the areas of the triangle. You will get 12.8 kilonewton meter. Once you have acquired the midspan moment, you will repeat the same process for the following stretch of the beam. Since the entire frame is symmetrical, the values that you obtain here, it shall be mirror to the span here. Theoretically, these two values should be similar. The slight difference is due to the decimal place. Imagine if you combine all this shear force diagram together, that will be the shear force diagram for the continuous beam. And if you combine these three bending moment diagram, it will give you the bending moment diagram for the continuous beam. Now that you have acquired the shear force and the bending moment diagram for the beam, you would like to calculate the loads acting onto the column. There will be two types of loads acting onto the column. First is the axial load, second it will be the moment. The axial loads acting onto the column is easy. You can get it from the shear force diagram. Why is it so? Because the reactions acting onto the beam, it shall be the loads taken by the column. Same goes to here and here. You will take these reactions for the column 1 here. Then you know the axial loads taken by this column, it will be equals to the reactions acting onto the beam, 22.6 kilonewton. As for this column, you will need to take the reactions from this stretch of beam as well as the reactions from another stretch of beam. That brings to you 32.2 plus 29.4 kilonewton. In total, you'll get 61.1 kilonewton. The other side, it will be a total mirror of this. From here, you will know the axial loads taken by each column. Next, we need to determine the moment taken by the column. Why do we need to calculate that? This is because from the table that you calculated for the moment distributions, on the column side, you use the stiffness to be the summations of the top and bottom column. Same goes here. The stiffness here, it will be the summations of both the upper and the lower column. That means when you estimate the moments taken by the column, whatever moment calculated here, it will be the total moment taken by both the top column and the bottom column. Since the top and bottom columns have the same stiffness, then we know that whatever moment taken by the column here, it shall be equally distributed between the two columns. Now the first column here carry 5.5 kilonewton meter. Being divided by 2, top column will take 2.75, bottom will take 2.75. Now if this column take only 1 kilonewton meter moment, half will go to the top, another half will go to the bottom. Now in case that the story height are different, your stiffness will be different. When your stiffness is different, then the moment taken by the upper and the lower column may not be the same. Whichever part of the columns have the larger stiffness will take more moment. Based on the calculations here, we now have the axial loads acting on the column as well as the moment acting onto the column. Bear in mind that this analysis is based on the moment distributions method, assuming the loads is maximum throughout the entire continuous beam. By right, you will have to test different load cases, such as all max, max min max, and min max min. You have to calculate everything, including the shear force and the bending moment acting onto the beams, and then carry forward for you to calculate the axial loads and the moment acting in the columns. You should use the most critical value in order to design for the reinforcement bar in the column.